This is intended to be a follow-up to that video that I already posted on YouTube, so I hope that you watched that. You might be a little bit lost today if you did not, more than a little bit. But let's talk about Sn1 and Sn2. Let's just kind of review the mechanisms and I'm going to do Sn2 first. That's why I wrote it. Substitution nucleophilic, bimolecular, substitution nucleophilic, unimolecular. This refers to the number of molecules in the slow step. So one of the differences between these is the type of halogenoalkane that is involved. Does anyone recall Sn2? Is that with primary, secondary, or tertiary ones? Yes. Yep. And the Sn1 are from tertiary. And then things that are secondary can do a mix of both. But let's take a look at the Sn2 mechanism first. So let's say, let's see, what do I want to do? Let's say we're going to do so bromoethane, let's say, and let's really focus on the carbon that's the reactive one is this one right here. That's the one that's attached to the bromine and has the partially positive charge. So let's really focus in on that one and to kind of look at the stereochemistry of it. And oh, whoops, let's not do it with a glowing thingy. Let's see, how do I want to do this? So we're really focusing in on that. And by the way, I'm going to draw the mechanism now. You don't necessarily need to show, I've looked at some mark schemes and stuff. It is not necessarily required that you show the stereochemistry inverting if it just asks you to show the Sn2 mechanism, but it definitely is possible that certain questions would ask you to do that. Or it is something you need to know. But we have this little carbon here, so the carbon's partially positive, the bromine is partially negative. The hydroxide has to come in from this side. So this is the slow step of the reaction. It's called the concerted mechanism. Basically, the bond is going to come from the opposite side of the bromine, so that's definitely important. You have to show that. And as the hydroxide is forming, the bromine bond is breaking. So then we have to show this transition step here. So temporarily, the carbon is going to have 5 bonds, and we're going to show that in a dotted fashion. And the OH and the bromine are always going to be on opposite sides of each other. And this whole thing has a -1 charge. And so if you can picture it, it's like an umbrella turning inside out. As this thing happens, these bonds here are going to shift around and flip to the opposite way. So our final product here. I don't know if this is the best drawing, but I think it gets the job done. Oh, whoops. Sorry, I messed that up. That guy's not there anymore. So we've got this thing just sort of flopping around and turning inside out. And so This molecule is not, this is not actually a chiral molecule, because remember, the carbon has to be attached to 4 different things. But if it were, or if that were possible, there would only be one optical isomer produced by this reaction. Just one. Because there's only one, there would be only one possibility, unlike the Sn1, as we'll see in a second. So same mechanism I was drawing on the previous video, I just am a little more careful about the stereochemistry in case we have to show that. Questions about that? So tying it into some of the stuff that we've worked in the workbook, this is a reaction that is first order with respect to both the halogen alkane and the hydroxide, because both are involved in the slow step. That's what leads to something being first order. So this is the slow part by far. Now, if we compare that to an Sn1 mechanism, let's this time say that we have tertiary halogen alkane like that. So an Sn1 mechanism, you cannot have an Sn2 mechanism because this carbon is actually completely blocked by these 3 other carbons right here. So it's literally impossible. The OH does not have room to fit to attack this carbon. So the slow step here is the spontaneous fission of that bromine, forming a carbocation here. Importantly, this is a trigonal planar shape, which means this carbon is now wide open for attack from either direction. And so we're going to get the tertiary alcohol here plus the bromine. And so again, this is not a chiral carbon atom, but because this is not attached to 4 different things, but you would find an even mix of both isomers in that case of the Sn2. Yeah.
Did you say it was UV light for the first step?
Say it was what?
Did you say it was UV light for the first step?
No. Just, you don't need UV light. This bond will sometimes just break. And so it's just breaking on its own, not necessarily with UV light or anything. Other questions about those? Yeah, go ahead. Well, I mean, if you set this up with the appropriate conditions, which is one of the things we're going to talk more about in just a moment, you know, the reaction will happen fast enough, but other than tweaking the reaction conditions, I don't know of any way to do it. But evidently an Sn2 mechanism is absolutely impossible with a tertiary because this is just completely physically blocked. So bonds do break. You know, don't forget that, especially if it's a little bit warmer, these bonds are all wiggling around and stuff, and they break and reform a little bit, especially a weaker bond, like a carbon-bromine bond. So it does happen. Other questions about that? Okay, so if you have your little note sheet, what we're going to add, as I said, ideally, we've already watched that video that I posted, but we're going to continue with that, and we're going to talk more about, as I was just discussing, some little tweaks and things like that that affect how these reactions end up coming out. So we're going to talk about basically different things, different starting materials or whatever that are going to influence the speed of this reaction and some other things. So this might make sense that if you're gonna, here we're talking about a substitution reaction where we're gonna swap out a halogen for a hydroxyl group. The weaker that bond, the faster the reaction is gonna be. So whether it's Sn1 or Sn2, but the weaker that bond, faster it's gonna be. Shorter bonds or stronger bonds. So generally what's gonna happen here is, all other things equal, the slowest reaction is gonna be with a fluoroalkane. The fluoroalkanes are pretty unreactive. They probably wouldn't react at all. And then as you go down the halogens down the periodic table, that bond gets weaker and weaker and weaker, and this reaction will go faster and faster and faster. So that's called the leaving group. So one of the things that affects how fast this reaction goes is the leaving group. Iodine is the best and the fastest. Fluorine is the slowest. So that's one factor that we could look at. And yeah, I would suspect you'd have a hard time getting fluoroalkanes to do much of anything with this. So the structure, as we've been talking about, tertiary are going to use Sn1 exclusively. Primary are going to use Sn2. The primary ones are not able to stabilize that carbocation. We talked about the inductive effect. They can't really stabilize that carbocation that's required in the Sn1 mechanism. But secondary will use a mix of the two. Sn1 reactions are going to be a little faster than Sn2 reactions, just in general, probably because there's only one molecule in the slow step. That probably helps. It's probably one of the reasons. And generally, tertiary halogen alkanes are going to be the fastest to react because they're going to have Sn1. They'll be faster than secondary, and then primary are going to be the slowest because they always have to do Sn2. So that's another factor. And you will have to evaluate the speed of the reaction at different times. We talked about this with regards to hydroxide specifically as the nucleophile. And in the old IB syllabus, you used to look at a bunch of different ones. That seems to have gone away, but they still want to, like, for example, you could potentially turn, in basically the same way, you could turn a halogen alkane to an amine, like using like ammonia as your nucleophile. But anyway, things with an outright negative charge are going to be a better nucleophile. Remember, nucleophile means loves electrons, better than something that has a partially positive charge. So hydroxide would be better than water, although you could maybe get a little of the alcohol with just water rather than hydroxide, but it would be slower and not as good. So then the other thing is the solvent choice. We've talked about solvent before. Almost all reactions, be they, unless they're gas phase reactions, be inorganic or organic, need some kind of solvent. And in the past, we've been talking about inorganic, so that's water almost always when you're doing inorganic chemistry. You got to, in the case of ionic compounds, you got to dissolve them. You got to get the ions. You need something for the reactant molecules to kind of move around in and collide with each other, and that's your solvent. And you got to pick the right solvent for a variety of types of reactions. If you're using nonpolar reactants, you want to generally use nonpolar solvents because otherwise, if you've got a nonpolar solvent and polar reactants that are not going to mix, they're going to like float on top. It's that whole like dissolves like thing. And same thing, you'd want to use a polar solvent if your reactant components were polar. So that's just in general. I think I mentioned also polar solvents can be protic or aprotic, which basically means can hydrogen bond or can't. So we can tweak the solvents, specifically in this case of Sn1 and Sn2, to do different things. So when you have some sort of ion in solution, it's going to interact with the solvent molecules. And protic solvents, remember, can hydrogen bond. They do a great job of what we call solvating both positive and negative ions because, like, if you take water, for example, the oxygen is partially negative. It can really close. I think there is actually space. Is there space to write this, what I have right here? Yeah, you should. Definitely. I like an intentionally left space, I believe. So water's polar, of course. It has a partially positive, partially negative side. It can hydrogen bond, so the water molecules, the negative side, is able to very closely approach a positive ion in solution, if that's what it's dealing with. But also, kind of by definition, the whole point of hydrogen bonding, or what causes it to be strong is that if you take these hydrogens here, they only have one electron apiece, and they're being pulled towards the oxygen. And so basically got a bare proton sitting there. And it can very closely approach negative ions as well. So they're very good at solvating both positive and negative ions. And depending on the situation, it might be good if that happens, or it might be bad. So depending on what exactly you want to do, you might want them to be solvating the things, or you might not. In the case of, this is just another picture of water. So like just a specific example of sodium ions and bromide ions being solvated by water. It's a little bit more detailed picture. So aprotic solvents, a common aprotic solvent might be propanone, which is more commonly called acetone. So here we have the sodium ions, and here we have, this is the oxygen on the ketone there. They can do a pretty good job of solvating positive ions because the oxygen can approach pretty closely, but they don't have a really strongly positive area. You know, these ones have the negative area with the oxygen. They don't have a really strongly positive area that can very closely approach these bromines. So good job solvating the positive ions, not as good of a job solvating the negative ions just in general. And unsolved particles, solute particles, are called naked. Questions about the difference between these solvents. So we're going to talk about how it relates to Sn1 and Sn2 in just a second. Okay. So for Sn2, you want to use polar aprotic. There's no such thing as non-polar aprotic, but I don't think. Yeah, that doesn't seem possible. Polar aprotic solvents are the ones you want to use. Why is that? Well, you don't want to use non-polar things because you're dealing with things that by definition are polar themselves, or hydroxide ions you're going to have to put an ionic compound, which are not going to dissolve well in non-polar solvents. So non-polar is just not an option. The reason why you don't want protic solvents is they do a really good job of solvating negative ions. So you'd have this hydroxide ion solution, which is negative. I wonder if there's a picture of this. Yeah, if you would have the hydroxide ion, which is negative, it's going to get caged by water or whatever hydrogen bonding thing you could do, and then it can't do that thing that it needs to do in the first step of Sn2, which is bump into the halogenoalkane because it's blocked by all these waters. So you don't want something that solvates negative ions very well. So therefore, you choose an aprotic solvent because it's going to leave the negative nucleophile free pretty much. And so it's going to be more free to move. And it says the effect is extreme. It's going to go about 1,000 times faster in aprotic solvents compared to protic ones. So you could use propanone, ethylnitrile. So you want something polar, but something that can't hydrogen bond. Questions about that? So yeah, again, here's the acetone trying to solvate the negative ion. Just can't do it quite as well or as efficiently, which is a good thing because you want this thing to be able to move and bump into stuff. For Sn1 reactions, you do want protic solvents because part of the step or part of the process is a carbocation, and they can kind of help stabilize that. The nucleophile isn't involved in the slow step. It doesn't really matter if it's caged in that sense. It's not going to slow down the reaction. So you could use water, alcohol, carboxylic acids. Questions about that? I think this is the end. So yeah, that's it for Sn1 and Sn2. There's some questions there at the end of the notes. That's what you should work on right now. Yes, Christian.
So for the Sn1, the Sn1 reactions, like wouldn't the phosphate solvent
Uh, well, there's a balance between so carbocations and things like that are kind of an unstable thing, and yes, potentially that they might do some blocking of that, but on the other hand, they also help stabilize it. So the net effect apparently is that you're much better off with the protic solvents. And I think because it opens up into that trigonal planar shape. It's going to be pretty hard to and anything can come from any direction. I don't think the blocking effect is going to be that extreme. Other questions about that? Okay.